Hey, math people, this is lecture 5 of the second chapter of Differential Calculus Calc 1. We're going to be looking at some intuition into the derivatives for sine and cosine. Then we'll naturally derive tangent, talk about all 6 of them, do some examples, and then see them in context, derivative-based context. So this video is for you, Taylor, or whoever you are. So be mindful to use the timestamps. Make this video actually worth your while, right? Click what you need. So if you want just examples, go to that. But if you want the intuition, here it comes. Let's math. Okay. All right. Consider the following. If I were to consider sine of x, which is like the baseline trig function in a lot of ways, right? At each pi over 2 multiple. Well, okay, just like talking about it from a general output perspective, it goes 0, 1, 0, negative 1, 1, right? I used to say like this goes middle, high, middle, low, middle. And then cosine is high, middle, low, middle, high, right? And then you complete like a wave of sine or a wave of cosine. So if I wanted to consider the slopes at these moments, we're just eyeballing for now, but if I look at 0, that looks to be like a slope of 1. It looks to be like an up 1, right 1. You can see it's like a 45-degree angle with the x and y axis. So that's like a slope of 1, we'll say, just on eyeball inspection. This is a horizontal tangent at pi over 2, so this is going to be a slope of 0. So output of 1, output of 0. See if you could do the other ones, and then go ahead and graph that. See if you can then connect the dots and create like a smooth curvature. What we're trying to do is derive the function that may be the derivative f prime of sine. So yeah, see if you can do that. So you're just sketching the estimated outputs of the slope at each of these moments in the graph. 3, 2, 1. Here it is. So yeah, the slope here is like 1-ish. The slope here is like 0-ish. Slope here is like negative 1-ish. Then it goes 0. Then it goes 1. Turns out those are the exact slopes, by the way. So what graph goes high, middle, low, middle, high? I mentioned it earlier. Oops. That one's cosine of x. So the derivative of sine is cosine. This isn't a proof. This is just an intuitive justification. That's all. Try to do the same exact thing with cosine x. I'm not going to do any lead into that. Just feel free to give it a go. 3, 2, 1, go. It's going to look like this, which is not quite sine. Negative sine is my derivative for cosine, right? It goes 0, negative 1, 1. Oh, wait, what? 0, negative 1, 0, 1, 0. So those are the slopes at those moments. And if you were to graph those, it doesn't curve out like sine does. This is sine right here, right? It's actually like the flipped over the x-axis version of sine, right? Because you have the hump up top, then down below, and it just kind of flip-flop down below, up top. It's a negative sine. It's reflected over the x-axis. Okay, so we have the slope of sine and the slope of negative, or the slope of cosine, which is negative sine. So slope of sine is cosine, slope of cosine is negative sine. Keep both of those in mind for when we now derive the slope for tangent of x. Because we know that tangent is sine over cosine. We know that this division is a quotient. And we know the quotient rule. So combine those ideas together. We know the derivative of sine is cosine, and the derivative of cosine is negative sine. Go ahead and try to apply quotient rule with that if you want to give that one an honest go. I'm going to show you that justification right here, right now. We know that tangent is sine over cosine, as previously said. If we do low d high minus high d low all over low squared, low is cosine, d high is also cosine, derivative of sine is cosine, minus high, which is sine, d low, derivative of cosine is negative sine. You end up getting cosine squared plus sine squared up top, which we know is the Pythagorean identity. So that's going to be 1 over cosine squared. Bring that back on up to the numerator. That's going to be the quotient identity, which is secant squared. So the derivative of tangent is secant squared. There's 3 more. You can use quotient rule and all this fancy jazz with the other 3. Let's not say we did. So here are all 6 trig derivatives. This is kind of what you came for. But I like to build the intuition, right? The big thing about math is that when is just delivered just like this, like let's just say I started the video like this. Let's just say you skip to this. You guys are missing out. There's something to say about developing like a base, a strong base, so that you can build beautiful building, or whatever the analogy I'm going for is. Okay, let's just do math. All right, we're going to try a few below. Okay, and I also kind of have fun with the variables that I use here. So practice using Leibniz notation when it's an equation like this. And then practice using Lagrange notation when it's a function like this. You can just ignore those instructions if you're not really vibing that. But I'm going to switch up the variables in use just for fun to practice the notations. But anyway, yeah, I'm going to just say round one, use the 6 definitions here. So anytime you're taking the derivative of, secant in this case, it will be replaced, or rather the derivative of secant is secant x tangent x. So don't forget your x's too. Sometimes in language I might just say, oh, derivative of sine is cosine. But okay, if we want to be picky, the derivative with respect to x of sine of x is cosine x. So just, keep all that good stuff in mind. All right, give it a go. 3, 2, 1. Lots of it's just using those definitions. So looking at secant x, that's just secant x tangent x, and then the derivative of a constant is just 0. Looking at the second term within, the first term is, the derivative of cotangent is negative cosecant squared, just based on these 6 definitions right here, is how I handled that first piece. Derivative of cotangent is negative cosecant squared, and then a negative makes a positive here. Derivative of x is 1. Look, listen, if you're like, what the heck is already going on? I'm just using these definitions that may have to be memorized, sorry. But there are lots of connections between these. So for example, all the co-functions are negative, right? Cosine, derivative's negative here. Cotangent, derivative's negative here. Cosecant, derivative's negative. The 2 quotient identities, the 2 quotient, functions, right? Tangent and cotangent. So this is sine over cosine, and this one's cosine over sine. Those are both squared. And then the reciprocal ones are 2 different functions. There's ways of mentally clumping these to make them not this crazy, what? We have to know 6 formulas after today? Yeah-ish. Sorry. It's fun, right? You're having fun? All right, looking at the next 4. So again, if you want to practice Leibniz for 3 and 6, and then Lagrange or Lagrange notation for 4 and 5, feel free. But you'll notice here you're going to have to start using some other rules, right? What operation is between x and cosine? What rule are you going to need here? What operation is between y? This needs to be a y. That's a y, okay? Between y squared and cosecant of y. So this is a good mini lesson here. Your variables have to match. If you're taking the derivative with respect to y, you can't just oh, I'm going to choose to take the derivative here with respect to y and the derivative here with respect to x. So pretend this is a y. Okay, can you do that for me? Thanks. Okay, 3, 2, 1. I'm going to show you the answers for each of these. So the added little rule here is that we need other rules. We need products. We need quotient. We need stuff like that. So okay, 3, 2, 1 for real. Answers. Okay. Yeah, I went ahead and I changed it here, but I didn't change it within the original notes. Okay, so again, both of these needed to be y. But looking at the first one, 3, this is just product rule, right? Derivative of first, keep second, plus keep the first, derivative of second. So combine like terms, if you can. You can't here, but just clean it up. You get cosine x minus x sine x. We would write this as dz dx, by the way. Okay, for the next one, that's just g prime of y, if we have g of y. So that needed to be a y, remember that. I said I hate quotient rule. I don't want to do it. You can't make me. I rewrote cosecant y as up top sine of y. I used a reciprocal identity there, if you remember that one. And then I just did product rule again. I did derivative of first, keep second, and then keep first, derivative of second. This is totally fine. Here's the thing. If you're like, man, I did a quotient rule, and I did the low d high minus high d low, and I got some negative cosecant y and cotangent y expression in there, and it's just this ugly big old fraction thing. Here's the thing. Your answer might be right. it may be algebraically equivalent to mine. So like technically what you can do is you can graph mine and then graph yours. If they overlap, it's a match and you have the same expressions. Remember on the AP exam, if you're taking that, you just need algebraically equivalent answers for the free response. Okay, this next one, I'm taking the derivative with respect to theta. That is a variable. And I used the product rule. I did derivative of first, keep second, and then plus keep first, derivative of second. Looks like this expression right here. Unfortunately, that's a minus in between, so you can't use Pythagorean identity. But this is r prime of theta. And then over here, oh, gross. I have a function of, or it's an equation, but it's an equation of u where it's defined with w on the outside. So this is dw du. So if you're like, whoa, 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 why is he juggling all? I'm just trying to learn trig derivatives here. You can think of this as y is equal to, and then these u's as x's if you'd like. But the idea is that eventually you get more comfortable with other variable types. But anyway, if we're just talking about the new math here, we're really just identifying this sign, and the derivative is going to be cosine when we get to it. But what I did was I rewrote the 2 over square root of u as 2u to the negative 1/2. Plus 1's just the plus 1, sine u is just the sine u. And then I noticed there's a product in between here. So I did product rule. So I did derivative of first, keep second, and then keep first, derivative of second. And then I didn't want to simplify that because I don't think you can. Okay, next little round here. So, you know, be kind with yourself. These are all intentional. These are all good. No errors here. So 3, 2, 1. All right. If you're looking at 7, you're like, whoa, wait a minute. Hold the phone. Cosine squared? What do I do with that square? We don't know. We need what's called the chain rule, which we haven't learned yet. But I know that cosine squared of a variable plus sine squared of a variable is literally just 1 by Pythagorean identity. So the derivative here is just 0. Crazy as that is. So we can verify that another time with what's called the chain rule. We need the chain rule. All right, looking at the next one, I didn't want to do quotient rule, right? So if you did quotient rule, that's fine. You can do the low-d-high stuff. I just brought secant up to the numerator. Actually, I took it a step further. I'm like, well, but tangent, I know tangent is sine over cosine. So those cosines just cancel. That's just cosine t. So if you went ahead and you did low-d-high, I mean, here, I'm gonna show you because I think it's worth the time. So we know that we could just use quotient rule. So if I were to run through this, quotient rule would be low-d-high. So low is secant. So this is going to be secant x, and then times, so that's low, and then d-high, derivative of tangent is secant squared. So we'll do secant squared of x. Is it cool with that? Yeah, it is. So that's low d-high, and then minus high, which is tangent, and then d-low, derivative of secant is secant tangent. So that's secant x, tangent x, and then that's all over low squared. Secant squared x. Oop, x. There we go. Hey, look at that. Derivative after just rewriting this as sine, the derivative of sine is cosine. Check it out. I mentioned this overlapping idea earlier, right? Well, they're the same thing, right? So they just overlap into the same thing. This quotient ruled expression for just keeping it in its form is the same thing as if you were to do trig first and then calculus. So you got to know trig. The identities you need to know. Pythagorean, quotient, and reciprocal. So that's like 2, I mean, I guess you can say 3, 2, and then like 6. So there are 3, 2, 6, whatever that is. 3 plus 2 plus 6 identities you need to know. Pythagorean, quotient, and reciprocal. Okay, next one is just a classic quotient. Nothing too crazy there. Now I was having a little fun with 10. I'm taking the derivative with respect to q, and g is my function, so g prime q. And derivative of tan q, oh, thank you, tan q, I think that's what I was going for there, is secant squared of q. Tangent of e is a constant, so the derivative of a constant, 0. Tangent of pi happens to be 0. So this is 0q, which means There's nothing here. So that's just knowing trig. So I was just having fun with this problem, to be clear. This is just 0. The derivative of 0 is 0. And then tangent of pi over 4 is 1. So this is just q. The derivative of q with respect to q is 1. That's fine. And think about how that kind of makes sense. How does q change when q changes? The same way. So 1. Okay, is there any more? Yeah, so now let's just see some trig derivatives in context. So here we have two limit definitions of a derivative, right? And what we know about the limit definition of a derivative is that this is f of x plus h minus f of x all over h. Hey, wait a minute. F of x is just right here. And I want to just take the derivative of f of x being sine. So that's your hint on that one. And then over here, it's kind of the same story, so keep that in mind. Remember, this is the derivative of f. And this expression here is f of x plus h and then minus f of x. So you can find f right here. In this particular case, you're plugging in an expression. So you're plugging in pi over 4 into whatever the derivative is for your function at play. 3, 2, 1. Okay. So this is just a fancy way of saying, what's the derivative of sine? It's cosine. Remember, this is the limit definition of a derivative, and f of x is right there. Same story over here. You just have a plus here, which is a little confusing. So if you subtract the negative, you get a positive. So this is take the derivative of negative cosine and then plug in pi over 4. So what is the derivative of negative cosine evaluated at pi over 4 is what this is. What did I do for the first step? Oh, first step, I just identified that this is just a minus minus. This is my function at play. The derivative of negative cosine is just sine. So I'm just taking sine of pi over 4, which is root 2 over 2. So we're using limit definition of a derivative for each of these. Lots of tangent line stuff. So if you want some tangent line practice, feel free to give these a go. I'm not going to spend too much time explaining these. What I would do is I would just graph my tangent line. If you're like, what? How do you get those? You can verify it graphically. 3, 2, 1. I'm going to show you. So yeah, it's the same old now. Like, hopefully you're with me if you're watching the videos and you're just like, okay, I've done enough tangent lines, but one last time I'll go through the process. What it is you take the derivative, plug in your x value of interest. That's your slope. And when you write this in point slope, your x naught is just the value they give you. How do you get that for the y naught? You just plug in your pi over 3 into the original equation. So you got to know some trig. You got to know some unit circle for some of these. 14 plays out the same. And then 16 is a normal line. So just remember to find the opposite reciprocal slope. 15 is fun because it's like find all the horizontal tangent. It's like, dude, what do you mean by find all the horizontal tangents? Aren't there like a whole lot of them? Because sine goes up and then down and then up and then down and then up and then down. So we find max, min, max, min, max, min over and over and over again. We're setting the derivative of sine, which is cosine, equal to 0. And you're just finding all those x values where cosine is equal to 0. If we're just circling through the unit circle, cosine is equal to 0 at pi over 2, then 3 pi over 2, then 5 pi over 2, then 7 pi over 2. So you're getting an infinite number of answers for this one. But it's cool to see the calculus meet the graphical and unit circle intuition. And this is just some fancy talk for it. It just keeps going. So 1, 3, 5, 7. Negative 1, 3, 5, 7. So where k is an integer, that's odd. I'm not sure how much you'll need this in your class. This was more of just a conceptual highlight of the fact that there's an infinite number of moments where you have a horizontal tangent for sine and for cosine. So for all the odds, over 2. Okay, these two are kind of fun. So hopefully you're with me on identifying some sort of sine-cosine pattern, right? You take the derivative of sine, it's cosine, but then when you take the derivative of cosine, it's negative sine. Is there some sort of like thing here? See if you can explore it, figure it out before I do it. Take the first 8 derivative of sine and then compute the 100th derivative of sine with that logic. 3, 2, 1. Okay, here's the pattern. It goes sine, and then cosine, and then negative sine, and then negative cosine. Circle back to sine, and we continue that pattern. The pattern's every 4. So if you take that 4th derivative, well, then you're just doing one full cycle, and you're just back to sine. So if you take the 100th derivative, you're doing 25 of those cycles, and you're going from sine to sine. I think that's it. Yeah, so that's it. Math on.